All right, I'm happy today to introduce the first speaker of this year's seminar series, Dr. Helcio Orlande. Dr. Orlande obtained his BS in Mechanical Engineering from the Federal University of Rio de Janeiro in 1987 and his MS in Mechanical Engineering from the same university in 1989. After obtaining his PhD in Mechanical Engineering from North Carolina State University, he joined the Department of Mechanical Engineering at the Federal University of Rio de Janeiro, where he was the department head during 2006 and 2007. He is the co-author of 4 books and more than 370 papers in major journals and conferences. He is a member of the Scientific Council of the International Center for Heat and Mass Transfer and a delegate in the Assembly for International Heat Transfer Conferences. He serves in the editorial boards of the journals Heat Transfer Engineering, High Temperatures, High Pressure, and the International Journal of Thermal Science. And I would like to add that Dr. Orlande was instrumental in helping one of my graduate students do the numerical analysis for his dissertation. And over the summer, we co-authored a paper that was published. And our collaboration continues, so I'm very happy about that. So Dr. Orlande, the screen is all yours.
Well, good morning all. Professor Margoron, thank you very much for the very kind introduction and also for the invitation to present this seminar. It's a great pleasure to me, a great honor to be here talking to you. I regret that I cannot be in person in FIU, but maybe in another time. Well, let me before I start, let me mention my collaborators in the works that I'm going to present here today, and they are listed here in alphabetical order. This list includes students and former students, as well as colleagues and good friends from different countries and with whom I have the privilege to work. This is the summary of my presentation. I'm going to talk about the motivation for this research, which includes the solution of inverse heat transfer problems within the Bayesian framework of statistics. Then I will present some of my past and current works related to the thermal treatment of cancer, and eventually present some conclusions. As you can imagine from the title of the seminar, the main motivation for this research has been the thermal treatment of cancer. The use of heat for the treatment of cancer can be aimed at a mild temperature increase of the tumor in order to make their cells more susceptible to the effects of other treatments like radiotherapy or chemotherapy. Alternatively, it can also be aimed at a large temperature increase of the tumor to kill their cells solely by the effects of heat. Within the medical community, these treatments are usually referred to as hyperthermia and thermoablation, respectively. Although the temperature level is not the only important factor to cause thermal damage to tissues, thermoablation is usually associated with temperatures above 50 centigrades, which causes cell necrosis. On the other hand, hyperthermia is considered when the tumor temperatures are raised to values around 41 to 45 centigrades. In this range of temperatures, a heat-induced cytotoxic response is produced, and it has been noticed an increase in the cytotoxic effects of radiation and chemotherapy drugs as well. However, temperatures below 43 centigrades can induce thermal tolerance on cells by the action of heat shock proteins. Recent advances in nanotechnology raised again the interest on the use of heat for the treatment of cancer by selectively increasing the temperature of tumor cells containing nanoparticles and reducing thermal damage to surrounding health cells. In fact, nanoparticles injected in the bloodstream, they tend to naturally accumulate in tumors due to the enhanced permeability and retention effect, which results from the hypermobility of the vascular endothelial cells and the impaired lymphatic drainage in tumors. After extravasation from the blood vessels, nanoparticles penetrate in the tumor mainly by diffusion and are then taken by the cells through endocytosis. Nanoparticles can be functionalized to target specific cancer cells and can be used as drug carriers. But toxicity might be an issue when the nanoparticles are picked up by cells of the immune system, which may promote inflammation. Nanoparticles of noble metals, they exhibit what is called surface plasma resonance, which in practice, it increases the absorption from an external energy source at specific wavelengths. Therefore, nanoparticles can be designed in terms of their material, shape, and size in order to become resonant at a particular wavelength of interest, as shown by these figures. It's also a great motivation for me, the application of inverse analysis in problems related to the thermal treatment of cancer. Inverse heat transfer problems, they deal with the estimation of unknown quantities appearing in the mathematical formulation of processes in thermal science by possibly using different kinds of measurements like temperature, heat, flux, radiation densities, etc. But why inverse problems are important for the thermal treatment of cancer? And here I would also add inverse design problems. There are many reasons, and here I list some. Hyperthermia and thermoablation, they require treatment planning or even a predictive control of the temperature distribution in order to concentrate damage to tumor cells, like any other cancer treatment. Therefore, mathematical models, they play an important role for the thermal treatment of cancer. Bioheat transfer models generally include many uncertain parameters. For example, the properties of tissues, they depend on the physiological state of the patient and exhibit a large variability from individual to individual. As we know, the estimation of model parameters is fundamentally an inverse problem. Nowadays, magnetic resonance or photoacoustic temperature imaging, they can be used for non-intrusively monitoring the delivery of thermal energy in tissues in real time. These techniques are also related to indirect measurements through the solution of inverse problems. Also, different bioheat transfer models, they have been proposed in the literature, starting with the classical model of Penis from 1948. All of them present some limitations in terms of the hypothesis that need to be assumed value. Similarly, there are different models available for the thermal damage caused to cells or tissues. Therefore, model selection and model calibration can be used to obtain accurate representations of all processes involved in the thermal treatment of cancer by the solution of inverse problems, through the solution of inverse. Our lines of action for the last 10 years have included works, and I would say actually most computational works dealing with the indirect temperature measurements, the model selection and model calibration, the development of nanoparticles, the analysis of hyperthermal and chemotherapy coupled treatments, and the design under uncertainty of the thermal treatment of cancer. For the solution of the related inverse problems, we have been using techniques within the Bayesian framework of statistics. In my opinion, the most complete reference for the solution of inverse problems with techniques within the Bayesian framework of statistics is this book by Kuiper and Sommersaal. I would like also to mention that I have been mainly working with Bayesian techniques after the visit of Jari Kuiper and Willy Coleman into my department back in 2005, when they taught a graduate course on the subject. For the solution of inverse problems within the Bayesian framework, all variables included in the mathematical formulation of the problem, they are modeled as random variables. Then techniques for the solution of inverse problems within the Bayesian framework, they can be summarized in the following steps. First one, based on all information available for the model parameters before the measured data is taken, we should select the probability distribution that appropriately represents the prior information about this model parameter. Then we should also select a likelihood function, which appropriately models the measurement theorems. And the likelihood function, it also involves a relation between the observations and the mathematical model of the physical problem under analysis. And as the third step, we should develop methods to explore what is called the posterior density function, which is the conditional probability distribution of the unknown parameters given the measurements. The posterior is related to the likelihood and to the prior by Bayes' theorem. And although this expression of this mathematical expression of the Bayes' theorem, it's actually attributed to Laplace. The density in the denominator of Bayes' theorem is called evidence, and it plays the role of a normalizing constant. But for most applications, the knowledge of the evidence is not required. Inverse problems can be solved within the Bayesian framework of statistics in different ways. For example, if the posterior is analytical, like in the likelihood, like when the likelihood and the prior they are conjugate, a point estimate can be obtained for the parameters as an optimization problem through the maximization of a maximum. Through the minimization of a maximum posterior objective function. For those cases that the posterior is not analytical or numerical integrations required for the estimates are not practical, Markov chain multicolor methods can provide a solution of the inverse problem so that inference on the posterior probability distribution becomes inference on its samples. This is shown as two examples here. This figure on the left presents the Markov chain for one single parameter. And after neglecting the samples before the chain reaches equilibrium, the statistics of the posterior distribution of the parameters, they can be calculated by using the samples of the Markov chain. This figure on the right, it shows the samples for a case involving two parameters. And we can also see that the chain, it eventually reaches an equilibrium distribution, and the samples of this equilibrium distribution is used for inference on the posterior distribution of the parameters. State estimation problems, they are also solved with Bayesian techniques. State estimation problems, they aim at the sequential estimation of the desired dynamic state variables by using the available measured data together with the prior knowledge about the phenomena of interest and the measurement devices. For linear and Gaussian models, the Kalman filter is the optimal solution. Although extensions of the Kalman filter have been developed for cases that do not satisfy any of these hypotheses, sequential Monte-Carlo methods, they are considered today as the most general and robust techniques for the solution of problems involving non-linear or non-Gaussian models. In these methods, which are usually called particle filters, the posterior density is represented in terms of random samples and their associated weights. There are also many situations where the likelihood is not exactly known and cannot be approximated in terms of analytical distributions. There might also be situations in which the calculation of the actual likelihood demands large computational times and resources, thus requiring model reduction or data compression. For these situations, approximate Bayesian computation can be applied because they can deal with measurements or total errors that may not be appropriately modeled in terms of analytical distributions, or the computation of the likelihood function can be very time consuming. Now, I would like to present some of our past and current works. In this example, a sphere containing nanoparticles mimic a tumor inside a healthy tissue. The tumor is heated by radio frequency, which is imposed by electrodes on the surface of the region. The transient temperature field in the whole region is recovered by solving a state estimation problem with the particle filter by using the measurements of one single temperature sensor located inside the tumor. This figure on the right upper corner, it shows the simulated measurements as well as the exact and estimated temperatures. It shows that the estimated temperatures are in better agreement with the exact ones than the measurements, as a result of the particle filter solution that also provides the uncertainties related to the estimated temperature. The figure below, it shows also the estimation of the temperature at the position inside the tumor, at which there is no temperature measurements available, and we can see that the estimated temperature is also very accurate. A similar result has also been obtained for a more realistic geometry of the abdomen, considering different, and in this case we consider that the tumor was located in the pancreas. And also we have applied the particle filter to a similar problem, but now involving the laser heating of a skin cancer. This figure on the right shows the estimation of the spatial distribution of the temperature along the center line of this region at a specific time, and it also shows very accurate estimates. And this is also the case for the temperature field in the whole region at two different times. These two figures on the top show the exact temperatures, while the other four below, they show the estimated temperatures obtained with 100 particles and with 250 particles. And that we see that the transient temperatures are quite accurate in the whole region, but particularly in the tumor region that is of major interest for the hyperthermometry. The application of the particle filter to the estimation of the transient temperature field in a region containing a tumor heated by a laser, it was validated by using a phantom made of plastic. A tumor was mimicked by a disc inside the phantom containing iron oxide nanoparticles that we have produced, and they are shown here in this figure at the top. And the internal temperature of the phantom, it was monitored by thermocouples. We can see this in the figure on the left bottom, which is a top view of the phantom. And this figure also shows the region containing the nanoparticles that mimic the tumor. The temperature of the surface of the phantom was monitored with an infrared camera, and we can see the experimental setup also in this slide, and a picture taken by the infrared camera while the phantom was being heated. The estimation problem, the state estimation problem, it was solved with the measurements of one single thermocouple inside the phantom. The measurements of other thermocouples and of the infrared camera, they were used for validation of the inverse problem solution. This figure on the left shows the measurements used for the inverse problem solution and the estimated temperatures, and they are in excellent agreement. The agreement between the estimated surface temperatures and the measurements provided by the infrared camera, which are shown on the right, they are also very good. But again, we should note that only the temperature measurements shown by the figure in the left, they were used on the inverse analysis. These previous examples of indirect temperature measurements by the solution of a state estimation problem, they involve the measurements of an intrusive sensor. I would like to present now two cases involving only non-intrusive measurements, which are provided by other physics. The first example, it deals with the magnetic resonance thermometry. Because it has been shown that the local temperature variation is related to the variation of what's called a phase shift, it's this delta phi, by this very simple equation that's presented in this slide. Although the direct inversion of this equation can be used for the measurements of the internal temperature variation, we have shown that the solution of a related state estimation problem reduces the measurement uncertainties. In this case, the equation is used as an observation model. This equation is used as an observation model, which is then coupled to an evolution bioheat transfer model. This approach allows the estimation of the temperature, also allows the estimation of the temperature itself instead of the temperature variation, which is given by this equation. We have applied this technique to an irregular region containing different tissues and a tumor, with heating provided by radio frequency imposed by electrodes located on the surface of the region. The solution of the state estimation problem, it also allows that the temperature be estimated in a mesh much more refined than that used for the magnetic resonance measurement, and also in regions where these measurements are not available. In this case, the figure on the left, it shows the mesh where the stated variables were estimated, while the figure on the right shows the mesh where the measurements were considered available in this region around the tumor. The exact and the estimated variations at a specific time, temperature variations at a specific time during the radio frequency heating are presented in these two figures. The figure on the left is the exact simulated, would be the exact temperature variation, and the one in the right is the one obtained by the solution of the state estimation problem. And they are in very good agreement, not only in the region where the measurements are available around the tumor, but actually in the whole region. The second non-intrusive and direct temperature measurements of internal tissues that I would like to present is the photoacoustic thermometry. Photoacoustic imaging relies on the generation of pressure waves inside the tissues, resulting from the absorption of the energy of a laser pulse. The amplitudes of the acoustic waves, they are proportional to the tissue's scattering and absorption coefficients in the laser wavelength, and they also depend on the Brunel's parameter, which includes the local sound velocity, the thermal expansion coefficient, and the specific. The temperature dependencies of these physical properties directly affect the amplitude of the generated acoustic waves. Then, photoacoustic pressure measurements have been used for the indirect measurement of temperature in biological tissues and the water solution. Such as for the magnetic resonance thermometry, photoacoustic temperature measurements can be obtained by direct inversion, but the solution of the inverse problem can reduce the measurement uncertainties. In this case, we solved an inverse problem to recover the spatial variation of the Brunel's parameter, which is a linear function of temperature. Oops, sorry. Okay, there is something going on. Okay. The case studied that we studied, it involved a skin tumor containing nanoparticles and heated by a laser. Another laser pulse was used to generate the acoustic pulses that were measured by transducers located over the skin. These are the results obtained at a specific time during the heating treatment by using the Markov chain Multicolor method, which provide very accurate estimates of the temperature in the region, even when we consider that the state estimation problem was solved with a very coarse mesh. And this slide, it shows the solution obtained with the Kalman filter for the sequential estimation of, which was implemented for the sequential estimation of the transient temperature during the whole thermometry. We notice in these figures that the effect of the non-uniform distribution of the nanoparticles, which was simulated in this case, it could be quite well observed because it resulted in the non-uniform heating of the tumor that could be accurately predicted with the solution of the state estimation problem. Although not related to cancer treatment, we have also considered the inverse photoacoustic thermometry problem as an auxiliary tool for the diagnosis of inflammatory bowel diseases. In this case, both the laser and the acoustic transducer, they are located at the tip of a shaft that rotates inside a catheter inside the bowel lumen. The simulated inflammatory regions that can be seen beyond this figure on the left, with high temperatures, they could be accurately identified by the solution of the state estimation problem, of the inverse problem, by as shown in the figure, this figure on the right. Now, I would like to move to another subject involving the thermal ablation removal of the tissue by laser heating. A numerical model was implemented and the direct problem was solved together with Professor George Dubikovic. And this figure on the right, it shows a comparison of our numerical results and the experimental data available in the literature for the ablation of rat liver. This figure shows an excellent agreement between the numerical results and the crater for predicting the crater position and shape that is called by this laser heating. On the other hand, the thermal damage models examined in our study, they could not accurately predict the sizes and shapes of the experimentally measured coagulation and necrotic zones. Models 1 and 2, they were the Arrhenius model, thermal damage model with different parameters, while model 3 was the two-state model of Feng et al. Then we implemented an inverse analysis for simultaneous model selection and model calibration in order to predict such thermally affected zones during the laser ablation treatment. The approximate Bayesian computation algorithm of Thon et al. It was used with simulated measurements, and these simulated measurements, they were obtained with the Arrhenius thermal damage model, which is model 1 in this figure. While this model also competed with the two-state model to represent the simulated measurements. Actually, we had a 50% chance for each model in the first iteration that we show in this figure. And this algorithm was capable of correctly selecting the model and also estimating the parameters, model 1, that were used to generate the simulated measurements in very few iterations, in 11 iterations. Actually, the model 1 is the only one selected at iteration 8, but the algorithm, it also demands fewer iterations after this one to calibrate the parameter values. And this algorithm, it was also used with actual experimental data that were obtained with an ex vivo muscle tissue, which was heated by a radiating heater. And the muscle tissue, it underwent thermal decomposition, but not actually tissue removal in this case. And the histograms of the estimated parameters of the Arrhenius model, they are shown by the figures here on the right. Now about the development of nanoparticles. Besides nanoparticles, nanoparticles of iron oxide that were used in the experiments with the phantoms that were presented before. The group of material science of our institution was led by a very good friend, Wilson Santos. They have also developed other nanoparticles for possible application in cancer thermal treatment. The focus here was the synthesis of nanostructured palladium and also palladium cerium, and also their respective hydrides. The use of hydrogen is very promising for the thermal cancer treatment due to its important role in physiological regulation, besides exhibiting good biomedical applicability and biosafety. Hydrogen is a therapeutic antioxidant that can reduce the hydroxyl radical. For the thermal treatment, hydrogen must be safely and effectively stored in nanoparticles to target specific cancer cells and also allow its controlled release. And then why palladium? Because nanoparticles of palladium hydride, they can store large amounts of hydrogen, and also they exhibit good biocompatibility, as well as high photothermal conversion efficiency in the near infrared range, as I'm going to show now. This figure shows the palladium nanotubes that were produced in this work. Their mean sizes were about 20 nanometers. And we conducted tests with nanofluids produced with those nanoparticles by irradiating the nanofluids with a laser a diode laser in the near infrared range. And temperature measurements of the surface of the nanofluids, they were taken with an infrared camera, as shown by these figures. And, actually, this is a thermal image that also shows, besides the heated nanofluid, all other wells containing distilled water that were used as reference temperature measures. The transient temperatures at the center points on the surfaces of the nanofluids produced with the palladium nanotubes with two different concentrations. They are presented on this figure here on the left. And we noticed that the effect of hydrogen in the nanoparticles, it was remarkable with the palladium nanotubes, which promoted a temperature variation of 32 centigrades at the final time for the largest concentration examined. While the regular palladium nanotubes without hydrogen, they exhibited a temperature variation around 25 degrees centigrade for the same conditions. And this red curve on the bottom, it's actually the temperature variation of heated distilled water under the same heating conditions, which at the final time it exhibits only about 2 degrees centigrade temperature variation. Then the same experimental technique was applied for an inverse problem with the Metropolis Hastings algorithm of the Markov chain Monte Carlo method to estimate the absorption coefficient of the produced nanofluids. The measurements were taken at the surface, again at the surface of the nanofluid with the infrared camera. And for the inverse analysis, we have used a model that takes into account convective effects inside the heated nanofluid. Why? Because the largest source term inside the nanofluid, it actually takes place in the region below the diode laser beam at the cylinder center line. The source term gradually decreased for deeper regions below the top surface due to the absorption of the laser beam by the nanofluid. And it also decreased radially and was very small at the cylinder lateral surface. The heat source induced a single natural convection cell, as shown by this figure in the middle. so that the fluid moved upwards in the central region with the larger temperatures and downwards near the lateral surface where the temperatures were smaller. And the temperature field at this specific time is shown by this figure on the right, and where we can also see that the temperature field is quite non-uniform. The samples obtained with the MCMC method for the absorption coefficient and for the absorption coefficient and for the global heat transfer coefficient at the surface of the well, they are shown by this figure, and these were the two model parameters that we had less informative priors. And these figures on the right, they show the estimated temperatures and the measurements, and they are a very good agreement, thus demonstrating that the model we used and also the parameters used estimated for the solution of the inverse problem, they are appropriate for all the phenomena involved in this case. Our objective in this work is to examine the decoupled hyperthermia and chemotherapy effects during in vitro diode laser heating of a culture of cells containing nanoparticles. We have developed a Multicolor parameter estimation and direct simulation for a simulated measurement, for a simulated experiment, which followed a protocol similar to that developed by Professor McGora. But for our case, we have considered, we have developed this combined multicolor direct simulation and inverse analysis framework with prostate cancer cells and under the effects of doxorubicin. And the choice for this cell and chemotherapy drug was due to our experience in the past with model selection and model calibration of the in vitro chemotherapy treatment. As shown by this figure on the right, that presents the iterations of Tony et al.'s algorithm for the simultaneous model selection, model calibration for the number of cells inside during an in vitro study. I'm about to finish, but before some of our recent works, they have focused on the optimal design under uncertainty for individualized thermal treatment. In this example, the design of the thermal ablation of a tumor by heating imposed with a high intensity focused ultrasound. It was performed in a probabilistic sense. Uncertainties in the model parameters and design variables, they were modeled by the prior distribution, while the likelihood it represented the desired outcomes in their acceptable uncertainties. Simulations were performed for this rectangular domain consisting of water, and also involving different tissues. And the rectangular region represented the tumor inside the muscle tissue. The tumor is represented in yellow. And the tumor was centered around this center line here of the region at x equals 0, which also the ultrasound transducer was centered, had a focal point on the center line. The samples of the posterior distribution for this case, they were obtained with a version of the Metropolis-Hastings algorithm with sampling by blocks of parameters, because we clearly have two distinct blocks of parameters. One is the physical properties of all the tissues, and the other one is the design variables, which in this case we consider only two design variables given by the heating time and also the vertical position of the hyphen transducer. The means and the standard deviations of a Gaussian likelihood are presented in these two figures. On the left, we we have the desired probability of dead cells inside in the region, which is almost 100% in the tumor region, and it's 0 in the region containing the healthy cells. And after we obtained we implemented the metropolis castings with sampling by blocks, we get this figure on the left that shows the mean values of the designed probability of dead cells. While the figure on the right, it shows the standard deviations associated, I mean, the uncertainty associated with this distribution of the dead cells in the region. Although that we see that most of the tumor, the probability is about 90 to 90%. The probability of dead cells is about 90 to 90% inside most of the tumor. While it's 0 in the region outside of the tumor containing the health cells. We also note that some parts of the tumor did not reach the desired probability of dead cells, and so all the design variables must be considered in future works. Just before finishing, I would like to mention some recent experimental results of Professor McGowan, revealing that the diffusion of nanoparticles into spheroids it increases with temperature. Fluorescence technique was used to directly measure the concentration of the nanoparticles in the spheroid. And the figure on the top, it shows that the nanoparticles were more concentrated in the periphery of the spheroid when the incubation temperature was 37 centigrades. But on the other hand, the fluorescence was more diffuse, and the nanoparticles penetrated deeper into the spheroid when it was incubated at 43 centigrades, as shown by the figure on the bottom. In cooperation with Professor Magor and also Professor Dulikravich, I have implemented the analytical solution for an spheroid containing an uniform distribution of nanoparticles, which is heated, which is uniformly heated. I mean, the top hemisphere of this spheroid is heated by a uniform laser beam, and while the whole surface of the spheroid it exchanges heated by convection with the Coulter medium. This figure on the top is the laser fluence rate inside the spheroid. We can see that it's larger at the top hemisphere, and it decreases as it is absorbed by the tissue and by the nanoparticles inside the spheroid. I mean, by the cells and the nanoparticles inside the spheroid. But again, it's almost uniform there, no? And this laser fluence, it results on this heat source that is presented on this figure on the left, at the bottom on the left. And with this heat source, we can compute the transient temperature, which is shown for a specific time here of after 200 seconds of laser heating. And the temperature inside the spheroid was practically uniform, but I will not. We still need to verify this solution. I think that's what I mean. I need to check this more closely and also compare with other solution techniques to actually verify this. Finally, some conclusions. Bayesian techniques, they are accurate and robust for the solution of diverse problems related to the thermal treatment of cancer. Why? Because the solution within the Bayesian framework of statistics, it's actually recast in the form of a statistical inference on this posterior probability density, which takes into account the probability distribution models for the measurements and also for the unknowns, which are constructed separately and also explicitly. The techniques for the solution of inverse problems, they were also used for the optimal design and synthesis of the hyperthermia treatment of cancer. In this case, we have used this Metropolis-Hastings algorithm with sampling by blocks. And because naturally we have two blocks of parameters, one for the model parameters and the other for the design factors. But our computational works have to evolve to more realistic test cases involving three-dimensional geometries with multiple organs. And also, these inverse techniques need to be applied with actual experimental data, particularly at the cell level and also tissue or spheroid scales. Because there are questions to be answered, how, for example, how individual cells and spheroids, they contain nanoparticles, how they behave when heated by lasers or other sources, and what are the local effects of nanoparticles. And have also shown that the temperature variations of nanofluids produced with the nanoparticles developed in cooperation with the material science department, nanoparticles of palladium nanopools and also palladium Sept. The temperature variations, they were substantially larger than those obtained with when heating distilled water, demonstrating the photothermal effect of these nanoparticles, and in particular those that were hydrogenated. But there's still some questions, like can these nanoparticles be used as hydrogen or drug carriers to tumors? So there's still a lot of very interesting, exciting work to be done. Let me thank Professor Anthony McGoran for inviting me to present this seminar. I really appreciate your invitation, Professor McGoran, and also the co-organization of the Wallace and Coulter Foundation Seminar Series. Thank you very much. The Department of Biomedical Engineering for you. I would like also to take this opportunity to thank my very good friend, Professor George Dubikrovich, for our very long collaboration. It's evidenced in several of these works that I presented in the seminar. And also, I would like to thank the hospitality of the FIU Department of Mechanical Materials Engineering for hosting me many times. But in particular, I would like to mention the last visit, which was during January, from January to March 2020. Actually, this visit should be 6 months long, but we had to cut it short because of the pandemic when FIU was closed and my university told me to come back to Brazil. And also I'd like to thank the support by different agencies of the Brazilian government, and this is it. Thank you very much. Thank you.
All right, thank you very much, Helcio, for a terrific presentation. We have some questions. If you want to ask a question, please enter it into the Q&A box. And our first question says, how critical is the temperature for hyperthermia treatment? Is it sufficient if above a certain threshold?
Yeah, this is a very interesting question, and I only mentioned those temperature levels in the beginning of my talk because they are more or less used for a general classification of the thermal treatments between hyperthermia and thermal ablation. But actually, not only the temperature is important, but also the time that the tissues or the cells, they are subjected to high temperature levels. So, and in this case, there are several models to represent this thermal damage. The most common one, it simply uses, it considers the thermal damage in terms of an Arrhenius equation. But there are other ones because this model based on the Arrhenius equation, it would be very nice, for example, if for one single protein decomposition. in the tissues, but actually for the whole tissue, it may not be appropriate. But again, all models are wrong. What we have to do is that some models work, some models doesn't, so it's our job to actually select models and calibrate those models that would represent that would give a good representation of process happening in nature, of course, by using by applying the parsimony principle or Oker razor principle, that the simpler the model, the better.
So another question from the same. This is a student, by the way, Sean Kong. If the what is the effect of the size on the tumor, on the on your results? The size of the tumor on your work?
Yeah, this is a very important question. And for example, when I have shown here these results for the design, you will see it's a small tumor. We did, for this case, it was a small tumor aligned with the high flow transducer, and we are now playing with different sizes of tumors and more realistic regions involving 3D geometries and also other organs. But it's also important. It's very important, and I think this will be this is very important specifically for this design of the thermal treatment for individualized treatment.
Yeah, and especially depending on the method of excitation of the nanoparticles, whether it's light, whether it's MR, whether it's ultrasound or something like that, that will all have an effect. Now, another question: if the if it's for the examples that are based on the delivery of a drug or a nanoparticle, can you comment on the effect of the selectivity of the absorption, or the the selectivity of the targeting of that hyperthermia agent?
We have not examined that at all. All those simulations, all those examples, they the presence of the nanoparticles inside the tumors, they were accounted for by effective properties, like the absorption coefficient of laser beam, or an increase in the or a modification of the electrical conductivity inside the tumor, and the same thing for other properties like the thermal conductivity, etc. So we haven't looked yet at the appropriate targeting of a tissue by a specific nanoparticle or something like that.
Right, that's my job.
and if you see all those experimental results that we were playing were with ex vivo tissues or with nanofluids. So we were mostly interested in examining if those nanoparticles would be appropriate or not for possibly a thermal treatment.
Right. So part of our next, what we're going to be working on is, together is accounting for the realistic concentration of the particles based on experimental methods. So now, if this is how much we can get into the tissue, what will the temperature be, right? So the next question from Dr. Raj: what magnetic field levels and frequencies are used to heat the nanoparticles? And how long does it take to reach, say, 50 degrees Celsius from the base temperature?
This is a good question. And for those examples here, these were in the radio frequency range. And all the other cases we have considered laser beams with wavelengths around 800 nanometers, because this is what we have for our diode laser. And this is there is also a window of absorption of our tissues and about this wavelength. And if you see some of those nanoparticles that they have been designed for hyperthermia treatment or for the thermal treatment, you see, gold nanospheres, they become resonant here about 500 nanometers, but like nanorods, they become resonant about 800 nanometers. So.
Yeah, in our studies, our own studies using dyes, near-infrared absorbing dyes at a concentration of 5 micromolar, we could increase the temperature from 37 degrees to 43 degrees within a minute at a laser fluence that has no effect otherwise on the tissue, that doesn't increase the temperature of the tissue or water at in the same time period. So another question, when is magnetic heating preferred over laser SPR heating, surface plasma resonance heating, and which is technically simpler and easier to implement?
Yeah, lasers, the laser beam, the laser fluence rate, which actually the laser flux, energy flux, it decreases very fast. It decreases very fast inside of the tissue. So, for example, here for this case, we can see large temperature increases for tumors near the surface of near the skin when we use the laser beams. But for example, for this case, which we had we simulated a tumor deeper inside the region. We have used radio frequency heating, and we have in this paper laser heating, you know, and surface laser heating was not capable of actually heating this tumor, even like and this is more or less 1 centimeter below the surface.
So there was another question that related to how in particular, how the laser therapy could be implemented, and the suggestion, which is correct, is that for SPR activation, laser activation, it really would be mostly appropriate under intraoperative procedures where you can expose the tissue, for instance, brain and brain resections, and then following up to ablate the remnants, things like that.
Yeah, it could be, for example, in this case of pancreatic tumor, you know, when people do the biopsy, it's very intrusive. It goes through the stomach or to reach the place where the tumor is. So the same procedure perhaps could be done to hit the tumor locally there
yeah, so the magnetic heating would probably be appropriate for deeper tumors. If you can't access it, SPR or laser-induced hyperthermia is not going to be practical if it's not an accessible tumor. But so our chair, Dr. Young, I'm sorry, didn't want to interrupt you.
No, just to also to mention that, for example, all those ablation of tumors in liver or the bone and lung, they usually use intrusive electrodes, and our objective here was always to consider non-intrusive sources of energy. So that's why the electrons, they are located externally.
Yeah, the ablation is usually with electrodes that are poked directly into the tumor that cook the tumor. And this application would be our application would be very appropriate for oral cancer, mouth, tongue, things like that. So our chair, Dr. Jung, Does the photoacoustic thermal print that you studied reflect what may happen to temperature in the eye when they do photoacoustic imaging? And are there any risks?
It's a good question. I don't know. Yeah, this photoacoustic imaging, I think that what we are closer to test in practice in laboratory by using rats is this diagnosis of the inflammatory bowel diseases. You know, because people already use a catheter to make images of the internal part of the intestine, and this can be used perhaps to also to convey the laser pulses, and also make perform the ultrasound measurements by locating a transducer at the tip of this shaft that would rotate inside the balloon. But we didn't go anything beyond this. I'm not sure about the applications to the eye.
And that she also asked, can you shape the diffusion of the nanoparticles? I'm not sure exactly what the question means. I guess maybe can you can you account for the diffusion of the nanoparticles, or can you affect the diffusion of the nanoparticles with the heating?
Yes, and I think that this is a big challenge, and I think that although the time scales, I think they are quite different. But for example, you know, and when we have this kind of symmetric or heating of the spheroid, if we can measure the temperature, maybe we can recover by inverse analysis the heat source, and through this we might be able to understand if the nanoparticles are moving towards the internal parts of the tumor of the spheroid. This is something that would be very nice, but on the other hand, what I'm afraid that this might not work is because the temperature inside the tumor, at least from this very preliminary, I will not take this very seriously yet, you know. But it looks like the temperature inside the spheroid is very uniform. So we would need very accurate measurements, a very accurate measurement technique to really identify temperature differences inside the spheroid caused by the presence of, or caused by the non-uniform distribution of the nanoparticles, or even caused by the moving nanoparticles during the heating process.
So that brings up a point, and we're out of time, but I want to ask one question, follow up on, so each of the different temperature measurement techniques that you talk about have different sensitivities, different resolution, different time responses, and how do those affect, I mean, how does your modeling take into account those issues in unknowns or in variability or?
Mm-hmm. Yeah, no, this is a very important point, and this is why we have been working with those Bayesian techniques for the solution of inverse problems for more than 15 years now. Because within the Bayesian framework, now you don't take into account only the uncertainties on the measurements, but you can also take into account the uncertainties in all model parameters or functions, including those that you suppose as known. Includes those that you judge, that under your judgment you consider them as known. They are known, but there's still some uncertainty related to them. Of course, this is very challenging because you have to model those uncertainties, and you have to model those uncertainties in terms of statistical distributions that might be appropriate to represent the associated uncertainties, or might not. So this is still very challenging.
Okay, well, thank you very much. We've run over time, but it was a great presentation and good question and answer. So there were a couple other comments in the Q&A that you could look at maybe and answer. And so I thank everybody for joining, and we'll get Dr. Orlande to his next meeting.
All right. Thank you. I really appreciate the invitation. It's my pleasure to be here today with you. Unfortunately, we cannot be all together, but
soon we'll get that.
Yeah, hopefully.
All right.